Hey guys, welcome to the first video of this channel. Pretty excited to start this channel to share a bunch of these cool, interesting puzzles and problems. And for this first video, I decided to showcase how I solved the November 2025 Jane Street puzzle. And essentially, we're given this grid, and we want to sort of create a subgrid that is the net of a rectangular prism. And we're given a bunch of constraints as to how we can create this net. The first of which is, well, to create the net, we have to cut away some of the cells, right? And so if you imagine that we have this grid printed out on a piece of paper, we can only, if we use a scissor to cut out a cell, we sort of have to come in through the edge of the grid, follow the grid lines in sort of a continuous way, and then exit through one of the sides. And so what that means for the net is that it has to be completely connected, and there can't be any holes in the net. Otherwise, we couldn't have cut it out, right? Because you have to enter from the edge. And the second sort of clue or given as how we want to create the net is based on these arrows. These arrows themselves, the cells with an arrow themselves are not part of the net, but they point in the direction or directions of the closest cells that are part of the net, right, within that cell's row and column. So for instance, this cell, let's do this cell that points upwards and downwards. Since they point in two directions, the closest cell that's part of the net has to be the same distance away from this cell, right? And then in the other two directions, left and right, the closest cell that is part of the net has to be greater than that. The distance has to be greater than that of the cells going up and down with respect to that cell. So, like, if the cell immediately next to them in the directions are part of the net, going up and down, then going left and right, the closest cell that's part of the net has to be greater than a distance of 1 away, right? And the last clue we're given is with these numbers. And these numbers sort of mean that within the 9x9 or the 3x3 square of cells surrounding that number, there are that many cells that are part of the net. Right? So for instance, there's 4 in the 9x9. There are 4 cells that are part of the net, and so 5 cells that are not part of the final net. And then these gray squares and circles sort of come in when you actually have the net and try to fold the rectangular prism, but that's sort of unrelated to finding the net right now, so we won't get into that. And so they sort of give an example puzzle of a much smaller grid, right? And they give the solution to it, and sort of you can see how it might fold into a final rectangular prism, and we'll eventually get a final answer from that. And so there's really two ways to go about solving this problem. The first of which is to code up, or is through a coding solution, where you sort of code in all of the constraints that I sort of just went over for each cell, and then through some like recursive solution, or using a very like fast SAT solver, if you know what that is, like Z3, to find a solution that simultaneously satisfies every single condition that the grid sort of contains. I felt like that was way too many conditions to try to sort of consider and implement. So the second solution, or the second way of solving this problem, which I did, was to do it by hand. And so we try to find the final net through a series of logical deductions of what the clues sort of tell us. And that's what I sort of want to showcase right now. And we'll use the snipping tool to sort of do this. And so uh, I'll use green to mark a cell that is part of the final net, and I'll use red to mark a cell that is not part of the final net, and I'll sort of refer to those cells as green cells and red cells now, respectively. And so the first thing to sort of notice that sort of kickstarts everything are these cells with the arrows, right? These intuitively should seem the most important cells. And in particular, we can look in the direction that the arrows are not pointing to. So if we look at this cell with the arrow pointing downwards, um, we can consider the cells immediately next to it that aren't being pointed to. And the idea is that they must all be red cells. Because let's say if this one was green, then that means the direction that the arrow is actually pointing to, which is downwards, the closest green cell has to be closer than one cell away, right? Because of this. But that's impossible, right? You can't have a cell that's zero distance away. Uh, and so that sort of immediately gives us that, the cells next to a cell with an arrow that isn't being pointed to must all be red. And that sort of holds for every other cell with an arrow, right? So we can um, immediately mark all of those as red, and I'll really try to go fast and go through that. And right from the directions, we're given that the cells with an arrows themselves, right, these should be red too, so they're not part of the grid. But I think there are too many cells with an arrow for me to do that. And I guess drawing an arrow over, or drawing over the arrows might sort of block our view of those arrows. And I guess we're also given that cells with a number are part of the final grid, so they should all be green. And so I'll go ahead after this to mark all of those green as well. Okay, those are all the reds done, I think. If we missed any, we can hopefully spot it later and just mark them red. And so I'll mark these green cells. Green cell, or the numbered cells green real quick as well. Okay, I think that should be all. So now what? There really isn't like a fixed place that you should start. Because there's so much, sort of you look around, see what you can notice, and then try to go from there. Oh, I missed some red cells here. So looking around, I guess we can try to come across this particular arrow, right? This arrow, we see that pointing downwards is immediately a green cell. So that means in the other directions that it points to, those cells must also be green because they have to be the same distance apart. I guess because they're like the closest cell to this cell with an arrow, and it's pointing in all three directions, so they must be the same distance. And so this green cell sort of affects this cell with an arrow now, pointing in this direction. So that sort of gives us that the cell is green. And then something else we can see is that, let's say for this arrow, right, it's pointing upwards. So the closest cell in the row and column to this cell is going upwards, which is 2 away. So in all other directions, the closest green cell has to be more than 2 cells away. So in particular, going leftwards, we see that this cell has to be red, and going downwards, this cell has to be red. And so now we come across sort of this patch of tiles or cells. And remember that in the very beginning, one of the first conditions was that the final net has to be completely connected. So all the green cells has to be orthogonally connected. Orthogonally meaning by an edge, right? Not diagonally, like this. So if you look at sort of this boundary sort of cuts off these tiles, right? So if any of these tiles were green, there's no way that we could make it connected to the rest of the green tiles that's outside of the boundary, right? So that means that these cells must be red. And that sort of goes for any closed group of cells that we can now sort of keep in mind, right? So for instance, we can see down here in this corner, these sequence of red tiles encloses all of these cells. So they must all be red cells as well. And I guess one thing that helps is that they're also next to an edge. So we can, I guess, consider like outside here also red. And so I guess we can try to look around and see if there's any like enclosed areas. This one was enclosed. Remember, cells with arrows are red. So for instance, we can look at this sequence, right? And so then everything inside there must be red. I think that's all I can see for now. Or I guess, right, this entire area is enclosed. So we have, these are all red. What now? Keep looking around a little bit. I guess we can start making use of the number condition as well now. So remember, for each number in the 9x9 or 3x3 square around it, there must be that many number of green cells. So if you look at this 5, we already have 4 tiles here marked as red. So there are only 5 tiles remaining. So that means that those 5 tiles must all be green. And so now this gives us something to work with, right? Looking at this arrow, this cell with an arrow, we have one green cell immediately next to it. So that means these 2 cells must be green. And looking at this arrow, going down must be green. And looking at this cell with an arrow, going right must be green. So let's see if we can make use of any other numbers. It's just 7, right? These 2 tiles are both, or they should be red because they're arrowed. So that means there are only 7 tiles left again. So because of number 7, we must have all of these are green. And I guess we also have a 9 here. So there are only 9 tiles in the 3x3, so that entire 3x3 is going to be green as well. Okay, so this green tile, looking at this arrow, the one above it is green, so the one below it must also be green. What else can we see? Okay, it's a little sneaky, but we can look at this tile or this cell with an arrow pointing upwards. Right, we have that. Let me switch to red. Pointing upwards, the closest green cell. All of these cells are marked, so the closest green cell is 1, 2, 3, 4, 6 tiles away, or 6 cells away. So going in the other direction, we know that the 6th tile must be green, and all the cells within it, or fewer than 6 tiles away, are red. So we have 1, 2, 3, 4, 5. All of those are red, and then that 6th tile is green. And so similarly, for this cell with an arrow in the bottom right corner, we have that the 1, 2, 3, 4, 5, 6, 7, 8 tiles are red, and the 9th cell is green. So going the other direction, 1, 2, 3, 4, 5, 6, 7, 8 cells are red, and then the 9th cell is green. And what else? Looking at this cell now in 3 directions, we see that it's pointing down. And I guess one subtle thing to note is that if it's pointing in direction, that means there's at least one green cell in that direction. But pointing downwards, there's only one cell that's unmarked. I guess that remains. So it must be green. And so that means all the other cells that it's pointing to in those directions are also green. And now we can make use of the connectedness again. In particular, if we looking at this cell, if it were red, then this sort of square of cells sort of traps this green cell inside, so it couldn't be connected with the other green cells. And so that means that this cell can't be red and thus must be green. And yeah, so this 4, it already has 4 green cells and it's 3 by 3, so that means the other cells have to be red. And so again, similarly, looking at this cell with an arrow, going downwards, there's only one cell left, so it must be green. And so the closest closest green cell is 2 cells away. So that means this one must be green, and this one must be red. And so this cell is green, so looking at this cell with an arrow means that this cell must be green. And looking at this 5, there's so in this 3 by 3, there are 1, 2, 3, 4, 5 green cells already. So that means this cell must be red. Yeah. Cool. Now what else? And I guess we want to try to finish off this section really quick, right? And so we can look at the unmarked tiles. We see that this unmarked tile is completely surrounded, so it's red. This unmarked tile is completely surrounded, so it's red. This tile here, I don't think we can deduce that yet, so let's just leave it unmarked. Let's mark it as like, I guess, yellowish orange for now. And so now we can look at these 2 unmarked cells, right? In particular, we see that this group of green cells here is sort of not connected to the other green cells here, right? And we see that the only way that it could possibly be connected is through this one green cell here, right? That's the only way to connect this group of cells with the rest. So that's what it means that this cell has to be green, which is nice, I guess. Yeah. Okay, so looking at this arrow now, you see that the closest green cell in that direction is 1, 2, 3, 4, 5, 6. It's the 7th tile. So going upwards, we know that 1, 2, 3, 4, 5, 6, 7 tiles are all red. Yeah. So I guess that immediately means that from this cell with the arrow, all other cells are red, other from this one unmarked cell, so it has to be green, and so this other tile has to be green. Right, so the 6 also means that these 3 tiles are green, because there's only 6 tiles left that are not red. Yeah, and so yeah, this 3 also means that this tile is green, and this arrow through this tile being green means that this tile has to be green. So this 2, you see that this 2 has two green cells already, so the other cells have to be red. And so the only way to connect this group of 2 green cells to the rest of the green cells is through this tile here, so it must be green as well. So now what? Okay, we can look at the 6, right? We already have 5 green tiles next to the 6. So there can only be one more, among these 3 unmarked cells, there can only be one green cell, right? So let's pretend that, let's say this cell was green. Then through this arrowed cell, it means that this cell must also be green. But then this 6 would have 7 green cells around it, which can happen. So we must have this cell is red, and so through this, again, arrowed cell means all of these 3 cells are red, and these 2 cells are green. And so this 6 is now satisfied, right? So that's pretty nice. So this cell being green means that this cell is green. Oh, I forgot to mark these sides as red because they're not being pointed to. Yeah, and so this we see this cell going rightwards. The closest green tile is 4 away. So going upwards, we have that this cell must be red, and we see that it's also the closest green cell is 4 tiles away. So that matches up. And so now that boxes in, or these box in these 2 cells, so they are red. And so now this 5, we see that there's only 3 unmarked cells left, and there's 2 green cells already adjacent. So these cells must all be green, right, to satisfy the 5 cells, the 5 adjacent cells. Okay, now what? Okay, so we have most of the bottom half done already. Okay, so this is very subtle again, but anything that you can notice, even if it seems very little, will eventually help you in some way. So if you look at this arrowed tile in the top left corner, see like going... Oh no, that doesn't help. Never mind. But this one does. If you look at this arrowed cell, going downwards, pointing downwards, the closest green cell is 4 tiles away. So in the other direction, rightwards, 4 cells away must be green. So you have that this is green. What else is there? So we can look at this arrowed cell. In the direction that it's not pointing in, the closest green cell is 2 cells away. So in the directions that it is pointing in, it has to be, the closest green cell has to be within 2 cells. And that really only leaves that the closest green cell can only be 1 tile away. So that means all of these cells are green. And so this cell is also green via this arrowed cell. And yeah. Now what? Ooh, okay. We can look at this arrowed cell. In a particular, this direction, or I guess like this cell in particular. Let's pretend that it is red. Then that means the closest cell in this direction is 2 cells away. The closest green cell is 2 cells away. So in the other direction, the closest green cell has to be 2 cells away, or this cell here. But we already marked it as red, so this can't happen. That means that this cell then has to be green, and so all of these 3 cells are green. So that helps fill in this bottom cell that we were missing before. And so this cell has to also be green then, or else if it were red, then it would trap this cell here. What else? What am I missing or not seeing? Okay, I guess we can turn our attention to this part up here. I guess this particular square. If this square was red, or more, I guess this square. If this square was red, then this section would be blocked off, right? So these would also be red. But then for this arrow pointing this way, there can be no green tiles or green cells, which we need at least 1. So that means that this cell must be green. And so this cell must be green. And so in order to connect this cell with the rest of the green cells, we must have this cell be green. Yeah. Yeah, that's right. Oh, okay. We can use. I completely forgot about the numbers. This 4 here already has 4 green neighbors cells, right? So that means the other cells have to be red. Yeah. And so, are there any other numbers that I sort of missed? Um, Okay, now we're a little stuck. A little tricky. Okay, we can look at this arrow. Or this cell with an arrow. Going downwards, there is a green cell within 2 away. Or there's a green cell 2 cells away. So in all the other, in rightwards and upwards, they all have to be within, the closest green cell has to be within 2 cells away. But this cell is already marked red, so it can't be green. So that means that this cell has to be green, right? And so all of these must be green in order for all of them to be the same distance apart. So that helps a lot. Yeah. And so we can look at sort of the pairing of this 4 and this 7. So we already have 2 adjacent green cells, so there can only be 2 other green cells within this 3x3, right? However, this 7 by the 7, looking at the 7 in this 3x3, we can only have 1 red cell, and so the rest of the cells have to be green. So let's say one of the red cells, like one of these 2 cells were red, right? It doesn't really matter which one. Let's say this one was red. So that means all of these cells must be green. But then this 4 would have 5 adjacent green cells, right? Which can't happen. And if instead this cell were red, we'd get the same issue. So that means that these 2 cells have to be green. And there is 1 between here. So yeah, we can't really decide that right now. How do you fill in the rest of this grid? Okay, really minor, but this cell is red because that encapsulates it. missing? No, something that I'm not seeing here. I guess we note that this cell has to be red on the left edge, due to this arrow having no green cells going this way already. I don't know. I'd really like to fill out sort of this section here, because it looks almost done, but we're just missing a couple of things, I guess. Oh, okay. So I don't know how I didn't see this when we were going over it, but this 7, right? There's only there's a red. This tile is technically red, right? Because it's an arrow cell. This tile is red. So that means, because since we need 7 green cells in this 3x3, and there's already 1 cell that's red, one of these 3 cells is red, and so the other 2 have to be green. And so if you look at the overlap with this 3x3 of the 4, then there's 2 green cells in this overlap, and there's 2 other cells outside of it that are for sure green, right? So that means this 4 will be satisfied by, I guess, like this region. So the outside region of that, or these 2 cells, they have to be red. And then, so if we look at this region of green tiles, it'll be disconnected from the rest unless this tile is green. Right. If it were red, then it'll be disconnected. So we have that this tile is green. Okay, now we filled that area up now. That's good. And I guess we can do something. No, we can't. Never mind. Yeah. Okay. I think we're good with that for now. No, actually, we can. Yeah. So remember we said before that within these 3 tiles, one of them is red, and 2 of them are green. If this one's red, then these 2 are green. But we said that if this one was red, then this would be a hole within the entire net, right? Which we can't happen because we're not allowed to cut that out. We can't cut this out if we start from an edge. So this tile must be green. And similarly, if this tile were red and this tile were green, then this would be a hole in the final net again, right? So that can't happen. So we have this tile is red, and therefore this tile is green. Okay, so we completed that area. That's good. Yeah, okay. What more? Not too sure. I don't know. I'm gonna start tweaking out if I don't find where to go from here. One, two, three, four. Should be one somewhere here, maybe. Okay, yeah. If we so this 5, right? When we look at this 5 and this 3x3, it already has 4 green neighbors, or 4 cells, 4 green cells in the 3x3. So within these 2 cells, there's 1 green cell and 1 red cell. And so let's imagine that this cell was red. Then this entire region will be boxed off, which we can't happen, or which we don't want, right? So that means that this cell should be green, and so this cell should be red. And so through this arrow, we have that these 2 are red, and so those 2 are green, because there's the closest is 2 away. Yeah, that's good. And so, looking at this cell, if it was red, right? If it was red, then we'd have this be boxed off again, which we don't want. So it must be green. Yeah, that's helpful. Can we really not do anything with this? Oh, I guess through this cell, right? In the direction they're 3 away, so going upwards, the third has this one can't be green, otherwise there will be an arrow pointing up. So that's red. That's good. Yeah, I guess we can't really determine this cell, any of these cells either then, can we? Yeah, I can't see anything, so we will mark these as orange for now. So I don't think we can reasonably determine them, or determine them via some logical deduction or something. So now what? I guess we can look at this 4 now, here. Or not even the 4. We cannot have this, or we can, I guess we can, never mind. Yeah. Yeah, these puzzles take a lot of time, and you just sort of have to sit here and keep staring at it until you see something. Which, I don't know, I feel like that's a skill to be trained, not something people are necessarily born with. Okay, it's this arrow here tells us that the closest green cell is 3 cells away. So that means going upwards, we cannot have any of these 3 cells be green. So that's really helpful, because then looking at this arrowed cell, we have that these 2 are red. So real quick, this one's closed off, so it's red. And so that means the closest cell is green, and thus this cell, it has to be green. That's good. And so to connect this region we have here, it's boxed off this way already. So the only way we can connect it with the rest of the green cells is through that cell. So it must be green. And still, right, this is still boxed off in this way. So this cell has to be green in order to connect it, in order to have a chance to connect it with the rest. And so this cell being green means that these 2 cells are also green via this arrow. So yeah, that was good. Quite a bit of progress. Ooh, this is so tricky. One, two, three, four, five. Am I missing something again? Okay, so we just have this upper right corner. Upper right corner left. Oh, okay. I guess I don't know if this one will lead to anything, but this is blocked off like this. So looking at this cell, this can't be red or else that gets completely blocked off. So that has to be green. And we know that via this arrow, because there is a green cell that's 2 away, there has to be a green cell that's 2 away here, or at least 2 away here. So within these, there's at least 1 green cell. Within these 2 squares, there's at least 1 green cell. So if this one is red, then that means this one is green, but that leaves a hole here, so that can't happen. So this one has to be green. So I'm curious what happens if we make all of these red. Then what happens? I mark them like this. I can't really see any contradiction coming up from that. So it seems like it's a possibility. So I guess you can't really rule that out. Um, I don't know. I don't know. Maybe we gotta use the numbers again. I've been sort of neglecting the numbers for a little bit. This 7 has one red tile, so we can only have one more red tile among the other squares around it. Okay, so we can just like work at it one by one. If this is red, then this would be green, which would make this a hole, so that can't happen. So this one has to be green. I think everything else seems possible. Yeah. Yeah, I don't know. One thing we can do, I think, that will help a little bit is to mark out the scissored cuts that would actually take place. Like if we were to print it out and cut along the edges we have so far. So starting from here, we'd come in through here, follow along this path. Remember, the greens should all be connected. So there shouldn't be, I guess, any islandish green that's floating around. I guess we said that those tiles were a maybe, so we'll keep them in for now. And then so this way we'd have to go like this. I think this one's a maybe, so we'll keep it in for now. I should probably make this a different color. That's probably a good idea. So I guess we have to stop there for now. Yeah. Okay, so I guess then we can see that this tile has to be green, has to be red, right? Otherwise, this would be green and this would be a hole, which can happen. So this is red. Yeah. Chat, I am stuck again. This isn't cool, bro. 1, 2. So there's 1 red tile among these 3 and 2 green tiles. I guess it could be any of them. Can't really tell. I don't know, man. Oh, am I? No, I'm not blind. There's 5. There's 1 red tile among all of this. If the red tile... Oh. If the red tile were here, then these would all be green, but then this would be closed off. Okay, so this one has to be green. Cool beans, bro. If this one were red, then this would be green and that'd be closed off, which is not good. So this one is also green. So this one's green. Oh my god, so much progress. Those are green. I don't want to finish this section off. So there's 1 red tile and 1 green tile. If this is green, then this is red. I think that's okay. Though it seems a little bit sus. I don't know. Though we can also metagame this a little bit. So in the end, we would like to fold it in a net. Oh, we want to fold the net into a rectangular prism. So we can sort of try to find like matching parts. And so one of the distinctive features that sort of pops out is this region here, right here. And we see that there's like this little part here, which looks a lot like this part here. And so, and then this part here looks a lot like, I guess, this part here a little bit. Maybe not. No, that doesn't look right. But no, at least the yellow part matches. But I don't think the green part really matches. Okay, never mind that then. Yeah, I don't know what I'm missing. 1, 2, 3. I don't know, man. This is hard. Oh, okay. Looking at this arrow, it's at least 1, 2, 3, 4, 5, 6, 7 away. 1, 2, 3, 4, 5, 6, 7. Right. So there has to be a green at least within this area, right? But these are all red. So that means there has to be a green within this area here. So there's a green within at least 2. So that means there's a green within this area as well. But there's only 1 square there. So this must be green, and so this must be green. And so this must be green too, in order to, otherwise this will be blocked, and so that green will be disconnected. That gives that all of these are green. We have that this cell must also be green too, because if it were red, then this would be blocked, right? So this is green. Okay, that's cool. Now what? Now what? Now what? Now what? I don't know, man. This is very, very tricky again. I don't know. You'd really like to find a contradiction somewhere. Damn, bro. I don't know. Okay, so for this 7, looking at the 3x3 around it, there's a red here. So there's one red and one green between these two tiles. Suppose this is red and this is green, and this is green, and this is green. Then this would have to be green, and this would have to be green. I do not see anything wrong with that. I don't think. Yeah, I can't see anything wrong with that. Not yet. Okay, what about the other way? This is green. This is red. This is red. This is red. So this is green. And what else? This is green. This is green. This is green. This is green. And so this is red. And this is red. Oh, but that can't happen. Okay. I'll walk through that again. So this is if that's green and this is red, then by these two arrows, this is red and this is red. But then by this four-way arrow, there's at least a green that's two away, right? But this one's blocked, so the green must be the two away self going up is blocked. So this must be green. These must all be green. But yeah. And then what did I say? What else did I mark? I marked something else. Oh, and then by this arrow here, this one must be green. So then by this 5, the one surrounding it must be red. But then this red is boxed in, so that's a hole and that can't happen. So we must have the other way around. So that one's red, that one's green, this one's green, this one's green. Yeah, that's really all I had for that case. That's unfortunate. 1, 2, 3. Really? You can't figure out which one that is supposed to be? Oh, okay, this 4... Was this 4 always like this? This 4, there's only 2 left, so these 2 are green. Did I really always not see that? Then if those 2 are green, then we can sort of look at the area bounded like this. Right. Sort of look at this bounded area. Or, I mean, like, how do I say this? What I want to look at is this 4-way arrow again. If these were all green, then this area would be bounded, right? And there's red in there, so that would be a hole. So that can't happen. So we must have these are all red. And so yeah, now this red part's connected to... Yeah, so we want it to be connected outside this way, right? So if it were green, if this tile were green, then it would be bounded again, right? So we need that tile to be red. Okay, so we can continue this boundary. Yay. We continue that boundary up there. Okay, so by this 5 now, we know that these 2 are both green. Yeah. And then... Anyway, in some way here for the boundary... Whoops, wrong color. we want it, it's either going this way or it's going this way. So in either case, it ends up on this line. We can just continue it around. Yeah. Okay, so we literally just have this very small spot now. Okay, I guess I want to look at this sort of group of numbers here. Let's try stuff. If this is all red, no, I want the other way. If this is all green, then the 5 is satisfied, right? So we have these 3 have to be red. But then this 7 means that all of these are red. That's okay so far. Oh, but then this 7 has 3 red neighbors, which can't happen. So we have that these must be red since that was our first assumption. So this is green. I think this one has to be. Oh, why am I coloring it like this? These are red for sure. This is green. And I guess like this entire region, something like here, right? If this tile were red, then we can just continue it up, and this would be bounded and cut off, which we don't want. So that means that this tile should be green. And so this 5 is not satisfied. We want these to be red. So that this 7 has 2 red now, so the rest of the tiles around have to be green. This 7 has 1 red tile right now, so we need another one. And then this 4 needs 1 more green tile. It cannot be this one, otherwise a red would go here and that's bounded off. So that's red, and that's green. Okay, we're almost done. Yeah, now what? I think we need this tile to be green. Otherwise, if it was red, then this would be bounded off again. Yeah. So this one has to be green. And so this 4 means that, yeah, if this was green, then all of these would be red, and we'd be bounding this part off again. So this one has to be red. And I think similarly, if this one is green, then these 2 are red, and we're bounding this part off again. So this one is red. And so now we must have that, right? This one is green, because if it was red, then we'd again have this bounding part. So this one is green to connect it. This one is red. I don't know about those 2. And then, what the heck is this? anyways, we can continue this. I don't know if we can determine which one of these should be inside. Because I think both of them should work. I think for these two are definitely a maybe. Let me draw some more boxes, bruh. Let me find a new color. I don't know. This seems a little bit weird. So this 4 means that at least one of these is a green, so it would be connected, right? So if this were green and this were red, that can't happen because from this 5, we know that one of these tiles is green, right? But in either case, we have either oh, I guess it can happen. Or we can't at least have this one be green, because then we have this bounding box. Or if like these were switched, we just like connect this part and it'd still be bounded. So this one has to be green. This one has to be red. Okay, now we can continue these edges. I guess these connect somewhere. So I guess these should just be a maybe. Wrong color. These are maybe, and I guess this one is maybe too. So that's all of it. And that was mainly that's all the hard part. Actually building the cube, how I did it was literally actually like made like I think it's like 20 by 20 grid, and or 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19. Yeah, I made a 20 by 20 grid from like graph paper and redrew this on the actual paper and cut it out. And building the cube actually isn't that bad. It's like much easier than actually doing this part. Mainly because Sorry, let me highlight these edges a little bit more. You can see a lot of the corresponding parts. Right, so in particular, you have this like 2x3 with a thing sticking out. You have that 2x3 and a thing sticking out. So when you actually build it, you can try to force this into that position, and then it'll eventually work out, I guess. Some other parts is like, I guess you have a cross here. Right, you have a cross thing here, a plus sign here, and you have a plus sign here in the bottom. So you can try to force that there as well. And yeah, it'll eventually like work itself out. Actually, I think the better way is you have this entire shape here, this Tetris looking shape piece here, fitting here, and that's immediately connecting to the 2x3 box I said earlier that actually should match this. But yeah, the point is that there is a lot of corresponding things, and you can sort of try to force things into it until it actually completely fits. And so eventually, I think when I actually did it, I think I got something pretty similar. Yeah, okay, so all of these were still undetermined when I did it when it first came out. So, okay, yeah, we got to the same place. And so these undetermined pieces are like, when you fold it, it'll become clear that, you know, they won't fit. They either will or won't fit. So you sort of just like cover them up, or like if they fit, cool. If they don't fit, then you just cover them up with some overlapping piece. And yeah, that's that. So once you cut it out, or I guess we can see that our net actually matches their solution. Yeah, they don't explain how they got it. They just give the solution. But you see that? Yeah, see, this undetermined part will eventually be part of it. Yeah, this one's not part, this one's part. One of these, both of these, or one of these is part of it. This one's not part of it. But yeah, it's the same. Yeah, you eventually fold it into like a 2x3 box, I think. Yeah. You get this, right? You cut it out. This is what I did. It falls into a 2x6x7, and I guess the numbers really quick. For these, gray circle should be directly opposite of another gray circle on the face, and then each gray square should be orthogonally adjacent and on the same face as another gray square. I guess like when you actually find the correct folding of it, it'll just like happen naturally, but you can also use it to like help you guide where a piece is supposed to go somewhere. And I guess your final answer is the product, is the sum of the numbered cells on each face, and then you take the product of all of them. And yeah, I guess you get that the final answer is this. That was 90 minutes. I did not expect that to be that long, but hope you guys enjoyed. I'll see you guys in the next video.